In this unit, we're going more over linear regression and residuals, plus we will be reviewing some normal distributions and some binomial distributions. So, problem 1. From experience, Japanese cherry trees tend to blossom early when spring weather is warm and later when spring weather is cool. There are some data on the average March temperature, Celsius, and the day in April when the first cherry blossom appeared. So you've got all this data. There's the temperature, and there's the day of the first cherry blossom. We need to describe the strength of the correlation. So let's go ahead and we're going to look at the data two ways, one with Staplet and one with the TI-84. Okay, to plot a scatter plot, let's go ahead and go to two quantitative variables in Staplet. Explanatory is Celsius. And again, you can put a comma if you like, not necessary. So I'm typing in all the data. Normally for a test, I will not make you type in a bunch of data, and I don't expect them to do it as well on the AP exam, because the issue with having you enter all the data is it's super easy to make a typo. And they're not really trying to determine if you're a good typist. So most times you're actually going to get an output. But for homework assignments, maybe even on a quiz, you should be able to put data in. So we went ahead and put all the data in, hit begin analysis. And there we are. They want the strength of the correlation. So all I have to do is come here and hit calculate correlation. And I get negative 0.8486. Remember, the direction should match the sign on the correlation. So here you can see that it is negative and it is strong. From 0.8 to 1, absolute value of that, anything in that region is considered strong. Negative 0.8 to negative 1 is also considered strong. Now we'll go ahead and look at the TI-84. Now we'll use the TI-84 to make a scatter plot. First thing we have to do is enter the data, hit stat, and then edit, or you can hit 1. Make sure you hit enter. Now you see I have all my data from before, from another problem. So if you want to clear this, you just go up to the top here, hit the clear button, and hit enter, and it's all gone. Same thing here. Make sure you go up to that top piece right there, hit clear, hit enter. Now, if I wanted to, I could have gone to L3 and L4 and then used those lists when I was doing my scatter plot. So let's go ahead and enter our data. It's 4, 5.4. Oh. So it looks like I have 15 data points. And let's go ahead and enter my second. Yes, and I have all my data is matching. Hopefully everything is properly entered. As I said before, usually we're not going to, on a test or a quiz, well, not on a test or an AP test, I think it's highly unlikely they'll expect you to actually enter the data. Now we want to graph it, so we're going to hit second, stat plot, and our plots are still on, so we're actually good. There's nothing I really have to change there. Everything's right, so I can just hit graph. But the scale's almost always off, so I'm going to have to hit zoom. And then remember, we're going to zoom stat 9, and then you can see that. Now, the problem is we can definitely see that the relationship is negative, and it definitely looks between moderate and strong. So let me go ahead and calculate R, the correlation coefficient. Now, last time I showed you how I had to go second catalog and then come on down to diagnostics. Oh, I hit enter. That's not what I wanted. So let me hit that again. Second diagnostics catalog. And I had to come down to the diagnostic on. You only have to do that after the memory's been cleared on the calculator. A lot of my students clear the memory when they take a test. Good for you. So odds are your calculator may have been cleared before you start using it. But if you want to see the correlation coefficient, you have to hit diagnostic on and hit enter, and then you can go ahead and run stat. You only have to do that one time, not every time you're doing a graph. So now I'm going to go ahead and calculate my regression, and I'll just do 4. It doesn't really matter if I do 4 or 8. And then you can see all the data. There's my R, which is negative 0.8486, which is definitely in the strong negative direction. Now we'll use the... Okay, so we have the output here. R is negative 0.848. Since it's between negative 0.8 and negative 1.0, it is strong and negative. Remember, correlation can never get more negative than negative 1, and it cannot get more positive than positive 1. Number 2, what percent of the variability in the amount of days till the first bloom in April is explained by the linear regression model using the average March temperature? So what we're talking about there is R squared. So we want that value right there, but that's a decimal value. We have to convert it to percent. So we would change it to 72%. Which of the following statements is true using the regression line from the date? So for every increase in 1 degree Celsius, this is telling me we're looking at our slope. So that tells us how the numbers of days changes for every extra degree in Celsius. And you can see that it goes negative. It's a decrease of 4.442 days. And that makes sense because the warmer it is, the sooner we expect to see the cherry blossoms. So there you go. For every increase in 1 degree Celsius, we expect to see a decrease of 4.442 days. Number 4, if the temperature is 4 degrees Celsius and the first bloom occurred on the 21st day of April, interpret the residual for this day. So we're going to need our equation, and I'm going to calculate the predicted value. So that's what that little hat over day means, it's predicted day. I could also write this out as just predicted day, equals negative 4.42, which was the slope we pulled from there. We multiply that by our x variable. In this case, that is Celsius. Let me go ahead and make sure I have my little laser pointer. So yeah, we take our Celsius, which is up here, and then we add our y-intercept, which is the b over here. And substituting in, we get 14.302. So that's the predicted value. And to find a residual, you have to go actual minus predicted. So some people say, oh, that's like AP, like an AP stat. So if that helps you remember which order, that's fine. So let's go ahead and substitute our actual and our predicted, and we get a positive difference of 6.7 days. So we have a positive residual. Now, you could memorize positive as over or under predict. For me, it's usually easier just to look at the actual and the predicted. So the actual is 21 days, but we only predicted 14 days. Did we actually under or over predict? We actually under predicted. It actually took 21 days before the first bloom, and we under predicted by 6.7 days. All right. So remember, again, you can memorize that under predict is a positive residual, or you could just say, hey, what happened? And I think that's the easiest way to keep it straight. So the model under predicted the day of the first bloom by 6.7 days. Is a linear model appropriate for this data? If it's the linear fit is good, if it's appropriate, then there should be no pattern in the residuals. So we're going to go ahead and take a look at the residuals using both Staplet and the TI-84. So I'm going back to Staplet where we have the data and then the scatter plot. If you want to see the residuals, you need to hit click calculate the least squares regression line. So I clicked on that, and you see that we get not only the scatter plot, but we also have the residuals. So this is a dot plot of the residuals, and we'll get into that a little bit more later. But usually what we're doing is we're just looking at this pattern right here. And if there is no real pattern, if it was like super zigzaggy, you know, like it was real obvious, then maybe. or if it had a fan shape or some sort of odd pattern, then we'd say, uh-oh, we've got an issue with this. But this looks pretty good. All right, when you calculate the regression, so I'm going to go back, stat, calc, and line reg, we'll use 4 there. And what it does, see where it says, well, actually it doesn't, that's the equation, but what it does is it will actually go ahead and calculate all the residuals. How do I know this? We can go to second stat plot. We're going to go to that first plot there. And instead of plotting the y values, now I'm going to plot the residuals. So you hit second and list to change the list of data. And look at that, number 7 is the residuals. So now you're going to be plotting the residuals against the values of x. And then we hit graph, and of course we're going to have to zoom. So we'll hit zoom and 9, and there is your plot of your residuals. So if the linear fit is good, then there should be no pattern in the residuals. And as you can see from our graph, we don't have one. And that means, yes, this is a good fit. We have no pattern in our residuals. Okay. A study of weekly hours of television watched and SAT scores reports a correlation of negative 1.18. From this information, we can conclude that, well, correlation R can only take on values between -1 and 1. So there must be a mistake. A mistake in arithmetic has been made. Number 7, 9th grade students at the Webb schools go on a backpacking trip each fall. Students are divided into hiking groups of size 8 by selecting names from a hat. Before leaving, students and their backpacks are weighed. The data here are from one hiking group. Identify the correct scatter plot that shows how backpack weight relates to body weight. So I'm going to take a look at choices B and E first, all right? And both of these have no labeling on the axes, so that's a bad sign. Don't do that one. We've got choice C here, but it's missing numbers on the scale, so we won't even use that one, okay? So we're down to A and D. Now, the question, really the only difference between these two is there's a flip in the axes. One has backpack weight as the explanatory variable, and A has body weight as the explanatory variable. Well, the backpack weight should be a response to body weight, so it should be on the vertical axis. And if I've told you about my hiking hobby, I like to go hiking across Spain, and one of their tips is to have your backpack weight not more than 10% of your body weight. So you can see these backpack weights are pretty good, all right? So actually over here. So there you go. Some of these may be a little high. So like a 100-pound person shouldn't have more than 10 pounds. So these are probably for a real full-on backpacking trip. Whereas on the Camino, we don't have to go carry that much like a tent. Number 8, the number of text messages sent and the number of phone calls made in a sample of 100 students. They want us to identify the explanatory variable and the response variable if possible. Well, for me, there's no obvious relationship between the number of texts and the number of phone calls. I don't know which one would explain the other. So I would say, whoops, darn, how did I do that? There we go. I would say that there's no obvious relationship between the number of texts and the number of phone calls, so either variable could be the explanatory variable because each one could be used to predict or explain the other. All right. Apples grown in a certain orchard have weights that are normally distributed with a standard deviation of 2.2 ounces. What is the mean weight if 80% of the apples weigh less than 9.1 ounces? So good news is this is not conditional probability. However, we don't know the mean, so we have to use the standardized model. That's where the mean is 0 and the standard deviation is 1. We're going to be doing a z-score. Now, we're actually calculating a z-score because we know the area. The z-score is the value for the standardized model, and the area is the percentage or probability on the standardized model. Actually, that is true on all models, not just the standardized. So we're going to go ahead and go to Stafflet. So we're going to go ahead and use the normal distribution, and since we do not know the mean and standard deviation, we have to use a standardized distribution with a mean of 0 and a standard deviation of 1. Now you're probably thinking, oh, do we calculate an area or a value? Well, since we don't have the mean and we know we know there's an area of 80%, we actually know the area, we're calculating the value corresponding to that 80%. Since it's the lowest 80%, it's left tail, 0.8. Calculate value, and you can see it. We have a z-score of positive 0.8416. And if I actually draw it like that, there you can see it says z equals 0.8416, and it's the standard normal distribution. To find the z-score with the calculator, you have to go to second distribution, but instead of using normal CDF, you're going to use inverse norm, enter. Now the area we're looking for is 80% or 0.8. We're using the mean of 0 and 1 because we do not know the unstandardized mean and standard deviation. We actually know the unstandardized deviation, but we don't know the unstandardized mean, so we're using the standardized form here. Now we want this to be the lowest 80%. So we're going to leave it here at the left. Now, if you have a less fancy calculator that does not show these options, then left is actually the default, and that's the one you'd be fine with 0.8. Now, if you needed the right area, you'd actually have to adjust this to 0.2. So we'll go ahead and hit enter, arrow down there, enter, and you can see our z-score is 0.84, just like what we got on this tablet. So we have our z-score of 0.84. We're almost done. Now we're going to use the formula for z-score, which is value minus mean divided by standard deviation. So we know the value, we know the standard deviation, we know the z-score. So we are going to substitute in and solve for, let's see, we are solving for the mean. So here we go, 0.84, 9.1, don't know the mean. Go ahead and cross multiply if that's what you like to do, or multiply both sides by 2.2. And then finally, I'm going to add the mean to both sides and subtract this value from both sides. I'm going to go ahead and round it up to 1.85 now because I can see these are just to the hundredths place. And my mean is 7.25 ounces. Number 10, suppose two events E and F have non-zero probability. So you know they're not zero. And they're P and Q respectively. Which of the following is impossible? So I'm going to go ahead and come up with a scenario where A could happen. So I'm going to try and make sure that is it possible? If I can find that it's impossible, that it is possible, then I know that it's not impossible. So E and F could be very different outcomes, like from different things. For example, heads on a coin flip and greater than 2 on the roll of a die. So if that were true, then you'd have probability of a half plus probability of 4/6 would be greater than 1. These are not the same event or not the same scenario, so it's okay that the probabilities are adding up to greater than 1. And you could also say, oh, if you subtract them, they're going to be less than 0, and that's fine. By the way, you could always subtract probabilities and have them even be just change the order on them, you know, and then you could get it less than 0. So that B I've never seen as an issue before. If we divide probability by x is less than 2 and probability by probability of h, then we get a value of greater than 1. So I could have just rearranged these so C works well. And then getting a probability of x greater than 2, and I'm going to change my situation here and say getting an even. Those are not mutually exclusive and they are not independent, because if you know you got a 2, then you know you got an even. If you know you got an even, then your probability of having gotten a 2 is higher. Now, mutually exclusive means the probability of E and F occurring at the same time is 0. Independent means the probability of E and F equals probability of E times probability F. Well, since both E and F are non-zero probabilities, we're not going to get 0, so this cannot happen at the same time. So your correct answer is E. E and F cannot both be independent and mutually exclusive at the same time. Number 11. You want to take a simple random sample of 50 of the 816 students who live in a dormitory on campus. You label the students 001 to 816 in alphabetical order. In the table of random digits, you read the entries. So we're going to use that table of random digits to select our sample. So they want us to identify the first 3 students in our sample. Good, because I don't want to sample 50 students. 3 is sufficient. So first of all, I need to model 816 outcomes. So we'll need 3 digits at a time. So I'm going to rewrite the line broken up into 3 digits. We have 955, 929, 400, 769, 769, 335. Now, we only need 816 outcomes. You can see we've got some that are above here. And so we're going to make sure to say that we're going to ignore 000 and 817 to 999 and also any repeats. So if I cross those out for the first few, I get 400, 769. See how 769 repeats there? Then I get 335. So E is the correct answer. Problems 12 through 15. Thousands of travelers pass through the airport in Guadalajara, Mexico each day. Before leaving the airport, each passenger must go through the customs inspection area. I've flown to Guadalajara multiple times, and yes, there do tend to be buttons. Customs agents want to be sure that passengers do not bring illegal items into the country, but they do not have time to search every traveler's luggage. Instead, they require each person to press a button. Either a red or a green bulb lights up. If the red light flashes, the passenger will be searched by customs agents. A green light means go ahead. Customs agents claim that the light has a probability of 0.3 of showing red on any push of the button. Assume for now that this claim is true. Suppose we watch 20 passengers press the button. Let R equal the number who get a red light. And there's your histogram. All right. So first of all, what kind of distribution is this? Well, we know N is 20 and P equals 0.3. So I'm really tempted to think this is a binomial. So let's check the conditions. Binomial is red or green. We've got 2 outcomes. Independent. The claim is that it's independent, that the probability is 0.3. All right. Or you can also argue that meets the same. The number, N is 20. So we have a fixed number. So we're fine. And then they asked, does it have a binomial distribution? It does. N is 20 and P equals 0.30. All right, now we're going to describe the shape of the probability distribution. So my natural tendency is to check if I can use a normal distribution for it, NP and N times 1 minus P. And checking those conditions, we can see that NP is 6 and N times 1 minus P is 14. So we need both at least to be 10. NP is low, so that means it is slightly skewed to the right, okay? So you can see how it's kind of scrunched up right here, but then it's stretched out a little bit there. However, this isn't really asking me to check if I can use a normal approximation. If I was just looking at this visually, it is fairly symmetric. So mathematically, I'm tempted to say it's skewed to the right. Now, it's not strongly skewed to the right, and that's probably why we settle on this answer of D. It is fairly symmetric, which means this brings us up to something you're going to see in the future. When you're presented with a visual like this, even if there's a slight skew, and very slight, go with a fairly symmetric, because a lot of times, if you were just looking at this visually, and they said, oh, could we use a normal distribution here? You would say yes. So again, based on the NP and N1 minus P, we can say, yeah, there's actually a slight skew to the right. But for our statistical work, we're going to go, oh no, it's fairly symmetric. And I'm sorry about that, but that's actually, I had to go double check that we were sticking with fairly symmetric, even though I had the math to show me, well, that's slightly skewed right. I will not do anything like this to you, like on a multiple choice test where it's this close. What is the mean of R? So if you look at your math chart under binomial, you'll see this formula. So I just take N times P, and it's 6. So my mean is 6. If many groups of 20 passengers were selected, notice that N is part of the interpretation. The average number of passengers who would get a red light would be about 6 passengers. There you go. Then they ask us, what is the standard deviation of R? Again, look at your math chart. This is under binomial distribution. And substituting in, we get 2.049, which is this answer. And let's go ahead and go through the interpretation. If many groups of 20 passengers were selected, the number of passengers who would get a red light would typically vary from the mean of 6 by about 2.049. Last question. Tanya wanted to estimate the average amount of time that students at her school spend on Facebook each day. She gets an alphabetical roster of students in the school from the registrar's office and numbers of students from 1 to 1137. Then Tanya uses a random number generator to pick 30 distinct labels from 1 to 1137. She surveys those 30 students about their Facebook use. Tanya's sample is a simple random sample because, all right, so a lot of you are probably going to be tempted to pick C. It is possible to satisfy C with different methods depending on how it's set up. What's not possible with other methods besides the simple random sample is B. Only a simple random sample provides an equal chance for all groups of the same size. So the correct answer is